Welcome everyone to lesson 2.11 from Precalculus, which is all about logarithmic functions. So let's get started. Our big idea for today is really what are the characteristics of and the behavior of a logarithmic function. So to understand its behavior, we have to understand its relationship with the exponential function because they are inverses. They have very similar behavior because one is the inverse of the other, therefore the inputs become the outputs, and the outputs become the inputs. So those behaviors mirror each other, if you will. So one of the first big things to notice is anything that has to do with x now has to do with y. So if we look here, we have no x-intercepts for a non-translated exponential function. So we have no y-intercept for a non-translated logarithmic function. The y-intercept, 0, 1, becomes an x-intercept of 1, 0. The asymptote also changes. So exponential functions have a horizontal asymptote, where logarithmic functions will now have a vertical asymptote at the same value. Instead of y equals 0, it becomes x equals 0. Increasing and decreasing, because they mirror each other, those actually stay the same. If the base of the exponential is greater than 1, it's increasing always in its entire domain. The same thing is true for a logarithmic function. It's increasing as long as its base is greater than 1 for its entire domain. Decreasing, same thing. If the base value is between 0 and 1, it's decreasing on its entire domain. Logarithmic functions, 0 to 1 as its base, also decreases on its entire domain. Speaking of domain, the domain of the exponential, being all real numbers, now becomes the range of the logarithmic function. And the restricted range of the exponential, which is 0 to infinity non-inclusive, now becomes the domain. So this is our second actual function we get to play around with that has some sort of restricted domain that isn't negative infinity to positive infinity. Because we've already talked about rationals. We talked a little bit about radicals, but this is the second one that we're really going to spend a lot of time with. So a lot of that's great, and you can take my word for it, but I'd rather you didn't. I'd rather you look at the graph and try to come up and see these things yourself. If I look here, the blue function in both is the exponential, and the orange function is the logarithm. This is for a base of greater than 1, and this is for a base between 0 and 1. And you can see that they are mirror reflections of each other over the line y equals x, which is what happens when you take the inverse of something. The exponential function is 1 to 1. The logarithmic function is also 1 to 1, so they both pass the horizontal and vertical line tests. Same thing is true for the bases 0 to 1. And you can see the x-intercepts. You can see the domain come into play. You can see the range kind of come into play. Now, we do have to keep in mind that the exponential, the logarithmic function has this exponential curvature to it. So what that means is that this end here, specifically, is going to continue to increase. It's going to increase slowly. It increases and grows slower than a linear function would. But it is growing, and therefore, as the x goes towards infinity, the y is going towards infinity as well. For the bases greater than 1, we also see that this end is going down, but it's never going to touch the vertical asymptote of x equals 0. So this means that its behavior is falling along the right side of 0. So that's going to be important later when we start to describe the end behavior of these functions. The base is in between 0 and 1, or aka a reflection, has some interesting properties as well. So if we look, the left side is still going towards 0, and it's on the right side of 0, but the right side is going down to negative infinity forever. Again, decreasing slower than a linear function would, but I digress, it's still going down towards negative infinity. And we can reflect these, we can translate these, we can do a lot of things with these and modify some of that. But you got to keep in mind, what does the graph look like? Like, what are the transformations actually doing to our function? So this is where understanding what the function looks like naturally really helps with that. Speaking of transformations, we have to be careful with our transformations. So our transformations for functions that we learned way back when apply to all functions, and they apply to all functions in the same way. That's what's nice about them. Logarithms, like exponentials, have some weird behavior. One weird behavior occurs when we have a horizontal dilation by a factor of 1 over b. In this case, b is 2. And we haven't necessarily talked about all of the different properties of logarithms. So you'll get to play around with this a little bit later, but log base 2 of 2x is equal to log base 2 of 2 plus log base 2 of x, which means that a horizontal dilation by 1 over b is the same thing as a vertical translation up by a factor of 1, or a unit of 1. So, kind of interesting. It's important to realize what changes when we do our transformations. Vertical transformations don't change anything when it comes to the range in terms of what is the range of the function, because it doesn't matter if you add, subtract, multiply, or divide. If it starts as infinity, it's going to end as infinity. And reflections just mean negative infinity becomes positive infinity becomes negative infinity. So we're still always going to have this range of negative infinity to positive infinity unless we do some restrictions ourselves. The domain, however, is where we get to see that change, because this 0 here can change. It can be any number if we translate it horizontally, or the positive infinity can become a negative infinity if we reflect it. So we just have to keep that in mind when we do our transformations. The last thing I really want to talk about is the uniqueness of the end behavior. So this is the major function where the end behavior isn't necessarily negative in x towards negative infinity and x towards positive infinity. This is the first one where an asymptote stops the function. The function only exists on one side of the asymptote. So our asymptote by default is this x equals 0. So again, the default one, where the base is greater than 1, its limit as x is going towards 0 on the right-hand side. It doesn't exist on the left. So x goes to 0 on the right-hand side. That goes towards negative infinity, and as x increases without bound, so does the function. So that's the idea here, is that we only have the right side of a curve. We don't have a left side. There is nothing that exists on the left side of this asymptote. So whenever we do these transformations, we just have to keep that in mind. So the same thing would be true if we did a horizontal reflection. If we reflected it over the asymptote, so it only exists on the left side of the asymptote, well, then as x goes towards negative infinity, the function is going to increase without bound, or go towards positive infinity, or negative infinity if it reflected vertically as well. The right side, however, only exists on the left side of 0, so we have to approach 0 from the left to get the other side. So we have to use one-sided limits to describe end behavior for logarithms because they only exist on one side of an asymptote. So that was a lot of talking. Let's get into the grind. Let's actually look at some transformations and see what's going on here and their effects on the domain, the range, asymptotes, and end behavior. So we have a logarithm here, and we have a couple of things happening with this logarithm. So the first thing I'm going to recommend is, one, I would definitely make sure that my x is positive, and I would rewrite it so my x is first. So we can rewrite this as the natural log of negative x minus 4 plus 2. And this helps us identify what are the transformations happening. Well, we have a couple, right? We have a horizontal reflection. We have a translation. We actually have two. We have one where we're going right 4, and then we're going up 2. So not bad, 3 transformations. So domain and range. Range is always the easiest one to start with. Range, the range of a logarithm. It's going to be negative infinity to positive infinity because it doesn't matter what we do to it. It's going to end up being the same. Next up is the horizontal reflection. So we're reflecting it horizontally, which means that the domain doesn't go on to infinity. It actually starts at negative infinity and moves forward. Then we go right 4, so it's going to end at 4, non-inclusive. The 0 wasn't inclusive by default, so the 4 is not inclusive when we translate that way. The asymptotes, well, that's going to be vertical asymptote at 4, so we have a vertical asymptote at x equals 4. End behavior. We know that we have to look at x approaching negative infinity and x approaching 4 from the left. So the limit as x approaches negative infinity of f of x. So negative infinity, we reflected it, shifted it right and up. The left side is going to go up without bound. So that is going towards infinity. And the right side is as x approaches 4 from the left of f of x. That one would be going down towards negative infinity. Now, I can picture a lot of these in my mind. If you can't, there is no shame. In fact, I recommend it when you play around with transformations to draw what you think the graph looks like. Draw a rough sketch, see what it looks like, and after you're said and done, check yourself. What's the harm? Especially when we're practicing and playing around with these functions and the transformations. If I look at this function here, it has 2 transformations, or 3 transformations actually, and we don't have to do any funny business of cleaning anything up to make sure that we distinguish what they are. So we have a negative here, which would be a vertical reflection. We have this 2 here, which means we have a vertical I missed the C. Vertical dilation by 2. And then we have this minus 2, so we're going translation right 2. So if I were to draw a rough sketch, I know that it went right 2, so we're going to have some sort of asymptote there. It's a vertical reflection, so it's flipping this way, and it's a dilation of 2, so it's got some sort of behavior like this to it. So essentially, that's what we're looking at. That's what we're playing with. So let's describe all of these aspects. The range, again, is the easy one. The range is negative infinity to positive infinity. We can see that from our sketch. It's increasing and it's going up and down without bound. Domain, we can see we're on the right side of 2. So we're going to start at 2 and go to infinity. And then our vertical asymptote is very clearly at x equals 2. The right and left sides, those are easy to pick up as well with a picture. We have the limit as x approaches 2 on the right-hand side of g of x, and that is approaching infinity. And then the right side is the limit as x approaches infinity of g of x would be negative infinity. Because the default one would be increasing without bound, this increasing over its entire domain. This one, being a vertical reflection, is decreasing over its entire domain. So that makes sense that we're starting at infinity and ending at negative infinity. The last one here, I even put a little star next to it because I don't like how it's worded, is ambiguous in the way it's defined. And I really want us to explore the difference between those two definitions or what they actually mean. I'm going to specifically say which one it is for this case, but in the future, like next class, I want us to really, really talk about this function and what are the ramifications of the different notations. So there's 2 ways to interpret this. This could be log of x minus 5, whole thing squared, or this could be log of x minus 5, and that is squared inside of the logarithm. And you really can't tell. For our intents and purposes, if we ever see this, it is going to be the second one. It is going to be this one. It would be clearly defined for this one. I would make sure and tell you that it is this one because this one has a lot of, we'll call it weirdness. Interesting behavior is the way I would like to put it. So this function would always be positive, for example. What this would mean is it's a log times a log. And it's very, very interesting. So I'd love to explore the difference between these two in class, but right now, let's explore what this one's behavior actually is. So if we look at what's going on, we really, really can't decide. We don't know. It doesn't fit the rules, and the squaring is why it doesn't fit the rules. So let me explain to you what the squaring does. So the minus 5, the first thing we can say is this is a translation, and it is right 5. What is the squaring doing? The squaring is taking any input and squaring the result, right? What does squaring do? Well, squaring takes any number and multiplies it by itself. So positive times a positive, you get a positive, great. But a negative times a negative is also a positive. So this function's domain is quite strange. What it's essentially doing is it's dilating the function by an inconsistent value, and its mirror reflection is also present. So this is interesting. So we have some sort of dilation. And I say it's an inconsistent value. It's actually consistent, but we'll talk about why later. It's a dilation by something vertically. Or you can say horizontally. It really doesn't matter. It's a dilation by something some way. But it's also reflecting it, but keeping the original image. So it also adds its horizontal reflection to the curve. So what do I mean by this? I mean by rough sketch standards that this, we have an asymptote here at 5, that's what we'd expect to see, some sort of dilation, right? We're getting its mirror image as well. Because if I pick something that's 1 more than 5, and I pick something that's 1 less than 5, well, I'm going to get 1 or -1. 1 and -1 squared both produce 1. So we're getting mirror images on both sides, and they're both shooting outwards. So we get some really weird behavior. The range of this, we should know, -infinity to +infinity. The domain, look at the domain. Look at our sketch. What do you assume it is? It's -infinity to 5 and 5 to infinity. It's everything but what makes the logarithm 0, because the logarithm is never going to be evaluated by a negative number. 0 is the only problem. We have a vertical asymptote at x equals 5, and then I didn't give myself enough room, but our right-hand and left-hand side limits, well, those are interesting as well, because the limit as x approaches -infinity of, what is this? It's h of x is infinity, and the limit as x approaches infinity for h of x is also infinity. Both ends are going up. The middle is what's decreasing. It's just very interesting, and we can talk more about it in class, and I would love to. If you have any questions about anything that we discussed, make sure that you ask me. Otherwise, I'll see you in the next video.